Alright, so now we know the Laplace transform of t to the alpha is equal to gamma of alpha plus 1 over s to the alpha plus 1. And the gamma function has nice properties. So if we want to calculate the Laplace transform of the square root of t, we know the square root of t is t to the 1/2. And based on the result we just found, this is equal to gamma of 3/2 over s to the 3/2. We don't really know what the value of gamma of 3/2 is, so we use the property of gamma function. So this is equal to 1/2 times gamma of 1/2. So this is a very special value. You should know in heads. So gamma of 1/2 is actually equal to the square root of pi. So now we can find the Laplace transform of this function. So it's 1/2 times the square root of pi over s to the 3/2. Right, so let's try to find the Laplace transform of an exponential function e to the at. By definition, this is equal to the integral from 0 to infinity of e to the negative st times e to the at dt. We can combine the exponents, so this is equal to the integral of e to the negative s minus a times t dt. This is equal to 1 over negative s minus a times e to the negative s minus a t from 0 to infinity. Again, this is improper. For this to converge, we need s minus a to be positive to converge. So if we assume x minus a is positive, then the only term we need is the 0 part. So the integral is equal to 1 over s minus a. So the Laplace transform of the exponential function e to the at is equal to 1 over s minus a, and the domain is x minus a greater than 0 or s greater than a. Okay. And here we're going to introduce a very useful property of Laplace transform, which is Laplace transform is linear. Which means that if we take the Laplace transform of a times f of t plus b times of g of t, this turns out to be equal to a times the Laplace transform of f of t plus b times the Laplace transform of g of t. So just like derivative integrals, so this is a very convenient property. And we can easily verify this. So if we follow the definition, this is equal to the integral of e to the negative st times the whole thing. And then we can distribute. Because integral is linear, so we can split this into two integrals. And then take a and b out. This is the Laplace transform of f, and this is the Laplace transform of g. So it's not a hard proof, but it's a very useful property. So we can use this property to figure out the Laplace transform of some more functions. So if we want to find out the Laplace transform of hyperbolic cosine, well, we know the definition of hyperbolic cosine. This is equal to 1/2 times e to the kt plus e to the negative kt. Let's assume k is positive. And because we know the Laplace transform is linear, so we can split this into two Laplace transforms. So this is equal to 1/2 times the Laplace transform of e to the kt plus 1/2 times the Laplace transform of e to the negative kt. And we calculated both of these in the previous page. So the first one is equal to 1 over s minus k. This converges for s greater than k. The second one is equal to 1 over s plus k. This converges for s greater than negative k. So if we combine the two fractions, and let's take the smaller of these two. So this converges for s greater than k, and this is equal to, the common denominator is s minus k times s plus k. This is s plus k plus s minus k. So this is equal to 1/2 times 2s over s squared minus k squared, which is equal to s over s squared minus k squared. And this converges for s greater than k. So that's for hyperbolic cosine. And hyperbolic sine is similar, so we're not going to do the whole thing again. So the Laplace transform of hyperbolic sine of kt is equal to k over s squared minus k squared. And the domain is the same. S greater than k is the domain. All right.